Today we'll be going over AP Calc BC FRQ 2006 number 5. So number 5 says, consider the differential equation dy over dx equals 5x squared minus 6 over quantity y minus 2 for y is not equal to 2. Let y equals f of x be the particular solution to this differential equation with the initial condition f of negative 1 equals negative 4. Part A asks you to evaluate dy over dx and d squared y over dx squared at negative 1 comma negative 4. This first question is very easy because all you have to do is take the equation given in the original question, which is this, and plug in negative 1 for x and then negative 4 for y. So that gets you 5 times negative 1 squared minus 6 over negative 4 minus 2, which simplifies to 6. So 6 is your first answer. And then to find d squared y over dx squared, you take the derivative of dy over dx. So, taking the derivative of 5x squared, you get 10x, minus the derivative of this, which to find it you use the quotient rule, and you get y minus 2 times 0 minus 6 times dy over dx, all over y minus 2 squared. So simplifying that gets you 10x plus 6 times dy over dx over y minus 2 squared. And like for the first part of the question, you just plug in negative 1 for x and then negative 4 for y, giving you 10 times negative 1 plus 6 times the dy over dx at negative 1 comma negative 4, which we established was 6, over negative 4 minus 2 squared. And that simplifies to negative 10 plus 1, which gives you negative 9. So negative 9 is your second answer. Okay, on to part B. So part B asks, is it possible for the x-axis to be tangent to the graph of f at some point? First, we should note that the dy over dx at the point x comma 0 has to equal 0 in order for the graph to be tangent, because only if the slope is 0 will it touch the x-axis once. If the slope was positive, it wouldn't touch the axis at all, and if it was negative, it would just go right through instead of being a tangent. We're going to be doing something very similar to what we did in part A, which is to plug in the coordinates to dy over dx. And don't worry about x being a variable because it just stands for any arbitrary number along the x-axis. So plugging that into the equation gets you 5x squared minus 6 over 0 minus 2, which simplifies to 5x squared plus 3. And notice that 5x squared plus 3 is always greater than 0. It's always positive. So that means it will never equal 0, which gives us the answer no. It is not possible for the x-axis to be tangent to the graph of f because dy over dx is never 0 on the points x comma 0. Part C asks to find the second degree Taylor polynomial for f about x equals negative 1. Remember that the general formula for a Taylor polynomial is f to the n of x times x minus a to the nth power over n factorial, where a is the point of revolution and n is the degree. And since the question asks to find the second degree Taylor polynomial, we know that n is equal to 2. And so the formula becomes f of negative 1 times x minus negative 1, which is x plus 1, to the 0th power over 0 factorial, plus f prime of negative 1 times x plus 1 to the first power over 1 factorial, plus f double prime of negative 1 times x plus 1 squared over 2 factorial. And now we just need to figure out what these coefficients are. But luckily we actually already did that because in part A we found that f of negative 1 is negative 4, f prime of negative 1 is 6, and f double prime of negative 1 is negative 9. So plugging that into the equation, we get that the second degree Taylor polynomial is negative 4 times x plus 1 to the 0th power, which is just 1, over 0 factorial, which is also 1, leaving us with just negative 4, plus f prime of negative 1, which is just 6, times x plus 1 to the first power over 1 factorial, plus the f double prime of negative 1, which is negative 9, times x plus 1 squared over 2 factorial, and that gives you the coefficient of negative 9 halves. So that is your answer. Lastly, we have part D, which says to use Euler's method starting at x equals negative 1 with 2 steps of equal size to approximate f of 0. Show the work that leads to your answer. So Euler's method is a way of approximating points on a curve using many tangent lines. And the formula for Euler's method is f of x is approximately f of a plus f prime of a times dx, where a is just the term that comes before x. So if this was replaced with x sub n, a would be x sub n minus 1. There is another way of doing Euler's method problems without using the formula, but because you'll probably be under timed pressure during the actual AP test, it's good to have this formula memorized. The only thing you need to be careful about is making sure that you know when your delta x is positive and when it's negative. So in our case here, we start at x equals negative 1 and approximate f of 0. So we're traveling from negative 1 to 0, which is in the positive direction, and so we know our change in x is positive. But conversely, if we were traveling from x equals 0 to approximate f of negative 1, we're going in the negative direction, which means that our delta x is negative. We also know that our dx is 1/2 because in order to get from negative 1 to 0 using 2 steps, our change in x has to be 1/2. So now we just start plugging things into the formula. We start with f of negative 1 equals negative 4. Adding delta x to negative 1, we get negative 1/2. F of negative 1/2 is approximately f of negative 1 plus f prime of negative 1 times the delta x. That gives us negative 4 plus 6, which we found in part A, times 1/2, which is equal to negative 1. Adding delta x to negative 1/2, we get 0, and f of 0 is approximately f of negative 1/2 plus f prime of negative 1/2 times 1/2. We know that f of negative 1/2 is negative 1, but in order to find f prime of negative 1/2, we plug in the coordinates negative 1/2 comma negative 1 to dy dx. And that gives us 13/4. So plugging that into the equation, we get 5/8. That was the last part for question 5 of the 2006 FRQ, so thank you for watching.